One. Before I start the example number one and we go through the four different cases, I just want to give you a little piece of advice when it comes to induction. There's a couple things that tends to be misunderstood when we talk about induction in physics. A lot of times students look at this and say that there are different left-hand rules. They're not. You're just applying left-hand rule 2 and left-hand rule 3 according to creation of the current. Induction really isn't anything you did differently in lessons 2 and 3 when you talk about using current to create a force. Now what we're going to do is basically create the current by doing the force. We're just doing everything in reverse. So the key thing that you're going to need to do when you do these is the variations on the left-hand rules. First thing you need to find out, and the first thing you do in every one of these questions, is you need to say to yourself, am I producing a current by doing some sort of mechanical energy to produce that? Like a generator type question. Or am I using electricity to cause a force? Two totally different concepts. To use electricity to create mechanical energy is what we call the motor effect. To use mechanical energy to create electricity is what we call induction, or the generator effect. We don't look at this process mathematically. We're only going to look at the concept in this course. The mathematics is not part of the Physics 30 curriculum. So again, what I'm going to do with these two examples, we have a coil, and what you need to do is you always have to have the force opposing the motion. That's what Lenz's law states. It says that the force has to oppose the motion, then you can go and generate your current using left-hand rule 2 or 3. So when you look at the first diagram on example 1, we have a north pole coming in. So what we'll do first is we have to have a force to oppose it. So to have something opposing that, I would have to then have a north pole on the coil to create a force to oppose the motion. If the velocity is heading in towards the coil, then the force has to oppose it. And there's where the black arrow comes from. Well, since to create a force to oppose it, if it's a north pole coming in, that means it has to be a north pole of the coil to create that force to repel. Once you know that, you then use your left-hand rule. When you know the north pole, point your thumb to the north pole, fingers curl in the direction of the current. So there's my diagram showing my left-hand rule. And your current is coming down on the front. So this case, the current through the ammeter, which is measuring the current, would be either considered clockwise, or another way that you could say it is from right to left, or even just draw it clearly in the ammeter what the direction is. So you always use your second left-hand rule for coils, your third left-hand rule for long straight conductors. Looking at example B, now it's a south pole moving away. So I need a force to oppose that motion. So if the velocity is moving away, the force has to be back towards. Well, to attract it to the coil, I'm going to need then a north pole on the coil. To get a force to bring it back has to be an attractive force, north-south. Again, point your thumb in the direction of the north pole, your fingers curl in the direction of the current, and in this case, your current, because the coil's orientated a little differently in this diagram, still comes down on the front, but when you trace the current, it now moves counterclockwise or from left to right. You have to be really careful, and coils tend to be the most difficult because it's quite hard to see how the coil's orientated, and you need to really track the direction of the current. And my advice to you is always figure out what the current's going like on the front of the coil and draw those arrows like I did in red, and then just keep tracing it all the way through the ammeter and then figure out your direction from there. This could be from left to right, or you could say counterclockwise if you want to look at it as in terms of the entire circuit. So there's two examples using a coil. Always have the force oppose the motion. Thumb points in the direction of the North Pole. Fingers curl in the direction of the produced current. One thing I want to draw your attention to, notice we're generating a current without a battery. That's how you can tell you're talking about induction. Every of the other lessons would have you using some sort of electrical source, a battery, to create the current. I'm just plunking a magnet inside a coil and I'm creating current as a result. Now you don't create a lot of current, but you do generate a small current, and if you put more loops or you move the magnet faster, the current will increase as a result. Let's look at a couple cases where we have the third left-hand rule. Again, when you look at C, the velocity is moving to the left side of the page, so the force has to oppose the velocity. The magnetic field is coming out of the page. So when we orientate our hand, it should look like this. Force opposing the velocity. Magnetic field coming out of the page. So it should show your current in the wire going south through the rod. Another way to look at this, and I'll kind of draw it on here, is you're actually looking at the rod in the magnetic field. So the electrons would travel down to the bottom in this direction, and they would travel through the resistor. This would be the direction of the current. Now you may be thinking, why wouldn't it go the other route? Well, remember, the electrons need a path to travel. So there's some device, a light bulb or whatever device, that this rod's moving back and forth in an electric field, and this rod or this light bulb would light up as the rod moves. It doesn't go the other route because there's no path for the electrons to travel at the other end of the loop, so it'll go through your resistor because that's the path of least resistance. And it's important for you to answer the question. I've seen questions say, well, what's the direction of the current through the resistance? What's the direction of the current through the rod? So you really have to be specific, because the direction of the current through the resistor is north. The direction of the current through the rod is south. So you have to be very careful about where you're being asked to describe a direction. And with D again, force has to oppose the motion. So if the velocity is up, that means the force has to be down. Fingers in the direction of the magnetic field, north to south. So I've got my palm down, my fingers going from north to south. Then that should indicate that through the rod, the current is coming out of the page. Now that's not the greatest drawing in the world. I'm trying to draw that rod perpendicular to the magnetic field where the rod is in and out of the page. But you can see from my thumb that the current would be coming out of the page in this case. So the key with induction and finding the direction of the created current is to always have the force opposing the motion. Whether it's the motion of the magnet coming into the coil, whether it's the motion of the rod moving through a magnetic field, the key with induction is that you need a permanent magnetic field, you need a conductor moving through it, and then you're going to create a current. And all the examples in your notes and all the little video clips that I have in here, that's the common theme with every one of those questions. When you use the left-hand rules, force opposes motion, fingers still in the magnetic field, thumb still in the direction, Or in left hand rule 2, force opposes motion, thumb points to the North Pole, fingers curl in the direction of the magnetic field.